All right, thanks for letting us know. Okay, well, good afternoon, everyone, and welcome to the Mapping Bluff Erosion Potential on the Pennsylvania coast of Lake Erie webinar. My name is Sean Rafferty. I'm the Research Director for the Pennsylvania Sea Grant College Program, and I'll be serving as the host and facilitator for today's webinar. For those of you unfamiliar with the Sea Grant Program, we are one of 34 programs around the nation working to promote the economic and ecological sustainability of Pennsylvania's coastal resources. And we do that through research, extension, education, and communications. And today's webinar really builds upon a four-part webinar series entitled PA Lake Erie Bluff Recession, a deep dive into the science and latest resources that our program hosted in 2021. And all four of the prior webinars are available on our Pennsylvania Sea Grant YouTube channel. In the chat, in the beginning of the chat, I did copy and paste direct links to those webinars on YouTube. So feel free to copy and paste those. If that doesn't work out, I'm happy to send those along to anybody that's interested in viewing them. So the purpose of today's webinar, and really the last years of webinar, is to highlight research efforts conducted by both Penn State Barron faculty and Sea Grant staff aimed at improving our understanding of coastal erosion along the Pennsylvania Lake Erie coast. And so today we have Dr. Tony Foyle joining us. He's an associate professor at Penn State Barron. I hope I got that right, Tony, and department chair at environmental science, where he'll be discussing the Bluff Erosion Potential Index. This was a tool developed with funding from the Pennsylvania Department of Environmental Protection's Growing Greener program. And I've also invited our colleague, Mike Neighbor, who is at Penn State Barron as well, who did a lot of the background GIS work on this project. So if any questions come up related to that. In addition to the links, YouTube links in the chat, you should see a couple links to both the BEP index. So that's a direct link to the actual tool, the web-based mapping application. And then I also provided a direct link to the methods document that kind of describes the background information related to the tool. And so for the purpose to keep the webinar on track and moving forward, feel free to use the Q&A button at the bottom of your Zoom screen to ask any questions. And what I'll do is I'll hold any questions until the end. And as time allows, we'll go through and Tony and myself or Mike will try to answer all the questions to the best of our ability. So again, I thank you all for attending today. Some of you sound like you're in a foot of snow, so I'm sorry to hear that. Things were looking better in Erie, but then we got some more snow today. So hopefully spring is on the horizon. And so at this time, Dr. Foyle, I'll turn it over to you.
Yeah, thank you, Sean. So thank you all for coming. So today we'll look over a new erosion potential visualization scheme we've developed for the Pennsylvania coast. So I think as background, because some of you may not be familiar with our coastline, we'll just look in general at how bluff behavior is on our coastline, how it's managed, and review the index goals before we delve into what the index actually shows us, how it works, and then what some of the caveats are with the maps that we have produced as part of the project. So we're looking at this picture of the entire Pennsylvania coast. It goes from the Ohio side over here at the Ohio state line up to New York on this side. And the index covers the entire shoreline, the bluff shoreline, so it excludes the beaches and stuff of Presque Isle out here. So that's our sort of geographic context. We'll be looking at maps later. And if we have time, even if we don't, this map is now live on the PA Walter website. So you could look at that at your leisure if and as you become interested in it. So we'll move along and we'll get down to our next slide. So the goal of this index is to very simply build a simple non-regulatory web tool to help property owners and coastal zone planners visualize erosion hazards along our roughly 73 kilometers of bluff coastline. So that was it, to develop a visual tool so homeowners could look at potentially their properties, their watershed, to see visually how bad their erosion might be. And the premise of the whole model then is that physical processes, natural processes causing bluff retreat are integrated into mappable bluff changes over time. And we can map and track those changes, and that's what the BEP index does. The processes for us, there's a lot of them, but the main ones would be wave attack at the toe of the bluff, groundwater flux out through mostly the top half of the bluff, and then general background slope change, slope evolution, anything from creep, very slow, insidious change to relatively rapid, larger slumps. And every so often, in some of these slides, you might see the link below. That's just the web address for the online version of this map. So for context, Pennsylvania DEP, the Coastal Resources Management Program, has been tracking bluff retreat over at least 40 years. So this is a summary diagram. It's a few years old, 3 years old or so, but what it conveys is that over the past 40 odd years or so, you can see erosion varies quite a bit along the coast. Just looking at the graph here on the right, these are for each of the 9 municipalities, 8 or 9, and you can see erosion tends to be higher on the west, in our West County, because the whole area between New York and Ohio is actually Erie County. So the West County sees higher erosion rates, they're lower in the middle, and they start picking up again towards the backside, the east side rather. So this is roughly 40 years of change. I'll be using this term quite a bit. ARR is just short for the average annual retreat rate, and this is a 40-year number. So it gives us a good perspective on change over several decades. On our coast, we get all kinds of bluff failure mechanisms, and this is a USGS fact sheet, which shows the most common ones and basically highlighted in increasing ring thicknesses in red there, how abundant these things are on our coast. So the biggest ones for us are these rotational slides and translational slides that move a lot of material over large areas down towards the shoreline, whereas other things like down here in the bottom right, insidious soil creep occur, move small amounts all the time. It's like a crumpling carpet. And then stuff we don't get technically are rock falls, because we don't have a lot of our bluffs composed of a large fraction of rock. Our tallest bedrock on some of our bluffs is about 7 meters. So that's our least important one. So we got a whole spectrum of behaviors for bluffs on our coastline. Geologically, for what drives some of our change here are these controls, the patterns we see is the geology of the bluffs. And this is a cross section from the West County, showing us that our bluffs tend to have shale bedrock right at the bottom. It's usually at lake level or slightly above it, no more than 7 meters above lake level. So we've got a shale bedrock that's pretty resistant to erosion. And then on top of that, we get a very stiff lower till that maybe, I'm saying greater than 18,000 years. That might be more than 125,000 years old. It's overpressured, it's very solid. You can almost chip it with a hammer. So that behaves a little differently to the bedrock. And then above that, there's a much thicker section of newer glacial tills, over 18,000 years old. And that tends to be softer. And that's the material in which we tend to see a lot of these large rotational slumps and translational slides develop. Then at the top up here, we have former lake bed sands and silts. Okay, so that's where our aquifers tend to be in this top section up here, which basically causes failures to occur in those sandy deposits quite frequently. But they might not be huge failures just because poor pressure is driving the material off the bluffs. We've got these lake bottom sands, and when lake level used to be higher. And then right on top, we've got what are technically called high stand sands and gravels. They represent a time when Lake Erie was higher again. And this feature right here is out near Lake City. There's a similar one over near Northeast. And these were like ancient versions of Presque Isle, if you want to think of it that way. They're very coarse grained, gravelly strand plane deposits. So that's our geology, and that indirectly, makes gives us the preceding picture we saw, variation in the types of failures we see on our coast. So we can think about bluff retreat conceptually almost. So this is two schematic pictures showing, over the long term, what does it look like bluffs do? In the top picture, this is what we might see today. We walk out across our property, we look over the edge of the bluff, and we can see a beach. Sometimes we'll see debris. And then if we think back in time, maybe go back 100, 200 years, I think we're all aware that the bluff used to be somewhere offshore. So if you think of in long enough timeframes, centuries plus, we could say bluffs tend to retreat in parallel retreat mode. If we've got a long sampling interval, it'll look like it's just going back very regularly. Now, this is a scenario for a shoreline that doesn't have bedrock, which ours does, but so this might be the Illinois coast, Wisconsin coast. So in bluffs retreat, it's not just land loss up here, we're also losing nearshore materials. The nearshore tends to get deeper, it gets lowered by wave activity. make sure my sound is on. Good. So on a shorter time scale, it gets a little more complicated. And this is kind of on a time scale of decades to centuries. This is a publication by Zuzek et al. And Mickelson et al. Found similar stuff in Wisconsin, but it turns out the cliffs don't go back in parallel. They go back in sort of a zigzag fashion. Okay, so maybe I've just thrown some numbers on here, various time periods, time 1, time 2, time 3, time 4. What I'm trying to show here is over relatively long time periods, from time 1 to time 2, which is over, what is that, 50 or 60 years schematically, you know, we can have bluff steepening occurring. And what we've noticed as a consequence of that is we're losing bluff face material, but we're not seeing much bluff crest retreat up here on the top. And eventually this gets steep enough that it fails. And the bluff actually jumps back over a relatively short period, maybe from 2050 to 2055. We'll see a lot of retreat. And that's what property owners are aware of. They notice that they might argue, we haven't seen, you know, bluff erosion in 10 years, but it's because bluffs on a shorter time frame tend to do this. So it'll jump back to the time 3 or 2055 profile. And then then the whole thing recycles again. Now the waves will start attacking the base. So by 2100, we're now forward to time 4. So we've got this sort of, you know, zigzag step back in a landward direction, and it's not always a constant rate of crest retreat or shoreline retreat. It tends to be very sporadic, very variable. And going from time 1 to time 2, we've got very low average annual retreat rates. And then from time 2 to time 3, we've noticed very large and average annual retreat rates. And that's why it's good always to use the longest data range possible you have in bluff measurements, because then you get more realistic retreat rates that reflect reality. So Pennsylvania manages this through the Coastal Resources Management Program, but since 1980, the Bluff Recession and Setback Act has established construction setbacks, and they're called minimum bluff setback distances within bluff recession hazard areas on our coast. So everywhere there's a bit where there's bluffs, the bluff recession hazard area, and BRSA incentivizes property owners to not build on the edge of the bluff, but to set back their buildings a certain distance. And there's basically 3 sort of categories. The residential setbacks tend to be smaller than the commercial setbacks, and the commercial are smaller than the industrial. And what they do is they take the average annual retreat rate, say that 40-year average, and they look at a 4 municipality like Springfield in this slightly older version of the graph. It's 1.054 feet per year. They multiply that by a time frame. The time frame is going to be 50 years for a house, 75 for commercial, and 100 for industrial. So if you want more information on that, the DEP's municipal reference document is available online. It's got more of this kind of information. But I'm just mentioning this here because we'll come back to some of these numbers as we look at our BEP index. And the thing maybe to note for now is the red circle. We've got municipalities have the option of making their setback requirements more stringent. And so in about half of municipalities they have more stringent setback requirements, and tends to be the ones where the erosion problems are bigger. Just looking at Springfield and Girard, for example, they've got, you know, pretty well, Girard, you know, 3 times the state minimum setback. So we'll come back. I'll be referring to these numbers later, as I say, when we look at our individual hazard zones to see how they relate. Ohio does slightly different things. It monitors things differently, but one thing they also do is when they allow development on their coastline, they tend to push out these design models that coastal engineers are recommended to follow when they design things. So one part of the design is actually regrading the bluff slope. So formerly it was up here, was this kind of profile. They regrade it, and there's a standard sort of geotechnical slope of roughly 26.5 degrees. That's used a lot in slope engineering. So I'll be referring to that as part of our index because we use this number. We just call it the geotechnical stable slope angle, because the concept is a slope this gradual should be stable over long time periods, you know, the lifetime of a house or longer, or 2 or 3 generations of a house. So Ohio does that. That 26.5 number is going to crop up again. We can go to places like Wisconsin is leading the charge on this, but also California, New York, Oregon in particular, and the entire Lake Ontario and Lake Erie coast of the province of Ontario in Canada. They have a similar approach that they think about this stable slope angle, and they tend to prefer a more gradual one. We could call this a policy or planning-based slope angle. It's 18.5 degrees. And again, these numbers are pulled out of, there's a lot of literature on this, so that we tend to have in use either 26.5 degree slope or an 18.5 degree slope around the country. So what that means is Wisconsin was looking into using this to make more conservative construction setbacks. So what they do is they look at the average annual erosion rate over time, maybe 40 years like we do, or 60 years, times the duration of the property. It's 50 years for a house. And that will give them a construction setback or a recession setback right here. Okay, it's this distance. And if the present bluff face is here, they'll incorporate this 18.5 degrees and then say this bluff face is unstable. We're going to assume it's going to regrade down to 18.5 degrees, to which we'll add that then to our AORT. And then to be even more conservative, several states are looking into adding a minimum facility setback, which is basically just space to move in equipment to move your house if and when the bluff gets to your building. So the net result of all that sort of worst case scenario or most conservative scenario is you can build your house, the front wall of it can be way back here, a long way from the bluff crest. So technically it's way more secure or safe than it would be if it was just built back the average annual erosion rate times the duration of the lifetime of the structure. So that's occurring in several states. Wisconsin was leading the charge on that. If you're interested, Bayfield County is the one where most of that work is being done. They've done a lot of mapping on this. FEMA suggests something different, something similar. Here we have their sort of conceptual diagram on how, what these construction setbacks could look like on a coastline anywhere in the US where there's bluffs. This comes from work by Keeler in Wisconsin back from the late 90s. And it's referenced in some of these FEMA coastal construction guidelines. But what they're assuming here is, let's say we stabilize the bluff toe. Admittedly, we should stop most of the bluff crest retreat due to wave attack, pushing everything backwards. But at the same time, even if you do that, the bluff slope itself is going to try and regrade to one of these more stable angles. And it's a bit hard to tell what the angle is here, but it's something near that 18.5 to 26.5 degree range. So even at the federal level, then there's recognition that stable slopes are a good thing to sort of consider when you're thinking about more conservative setbacks. So returning to our BEP index then, so we'll look at some maps on this moving forward. So the premise again is we've mapped bluff retreat at 2850 transects along our coastline, roughly at about 20 meter spacings. And we're assuming that the data we collect is the integrated response of the bluff landform to hydrodynamic, which is wave, surface runoff, subsurface processes like groundwater. So, we're assuming there's a link between the geometry of the bluffs, what they are now, what they could be, and the processes that occur on those bluffs. So we use several or a bunch of pretty easily mappable physical attributes of bluffs. So the first thing we have in our model is the present bluff slope. And by present, the most recent data we have is from 2015. It's LiDAR data. So it's already, 7-year-old data, but everything going forward from this point in the talk, the present is essentially 2015. So we use the present bluff slope at each transect. It varies a lot from 15 to 72 degrees. If we happen to have a data transect where we couldn't extract the bluff slope, we assume the watershed average slope applies as a reasonable approximation. We use the long-term average annual retreat rate. So this is longer than the coastal zone management groups. One, just because we happen to have gotten data from the Corps of Engineers from 1938. So we can compare that with the 2015 data and get a 77-year rate. Okay, so it's long-term relatively, and that's good to have. If for one reason or another we can't have it, we can't get a particular transect, we'll just roll into that transect the average AOR 77 from that watershed. As we end up building this index basically by watershed, we've got roughly 69 watersheds along our coast. So if we physically characterize each watershed, that's an important sort of criterion in telling a bluff how it fails, how much water and that kind of thing is arriving on these smaller watersheds. We use the bluff crest elevation relative to spring 2015 mean lake level. That's just when the LiDAR was collected. We'll use some slope angles. So I've mentioned the 18.5 degree stable slope angle, the 26.5. We also use a watershed slope average. So we take the average slope for any one of those 69 watersheds and use that also within the watershed. We look at the presence or absence of bedrock or developed lowlands at the bluff toes. That would apply to most the largest areas, probably the Erie downtown area, where there's a lot of lowland development like Dobbin's Landing and so on the lakeward side of those bluffs. So we got to consider that that does take wave activity away from the bluff toe, and also makes the bluffs relatively shorter. They're not as high because the toe of the bluff sits potentially 10, 15 feet above lake level. And for geometry purposes, just to keep it workable, we assume the bluffs were relatively flat on their top part. So the inland areas or the plateau or the tableland on top is flat for about 250 meters going inland, which is as far more or less as our index stretches. And that's a reasonable assumption, because a lot of these bluffs have flat land on top. And if you're interested, another key point here is that this index is very similar to a hazards mapping scheme used by the state of Oregon. They've got a very similar visualization of their bluff hazards, because they've got bigger bluffs than we have. They face a more hydrodynamically active water body, aka the Pacific Ocean. So ours is very, very similar to those. It was very, it was part of the design of ours, the things we should consider when we're building an index like this. So I mentioned there's a lot of text on here, don't worry about it, but what we're saying in our index is that we've got these system inputs like groundwater, waves, gravity, runoff, and climate that drive bluff retreat. And they all have relatively different importances, just schematically shown here. They've got a lot of importance or some moderate amount or not much. And then they result in the things we see on the bluff slope, the retreat rate in particular. So that's our sort of linkage between geometry and natural processes that we use in this index. So when we think about bluff retreat, we've looked at this a little earlier, but another way of thinking about it is you can think of a bluff retreating over time. So this is today's bluff face here, the crest. This is after some time 1, time 2, time 3. We've talked about over the long term, it looks like bluffs might retreat in a parallel fashion. Okay, so very simple geometrically. We just happen to have some complications in here with different materials making up the bluffs. If you think about it, these lines we're never going to get a perfectly straight bluff face, because the sand falls off here, glacial tills slump. It's always an irregular, bumpy surface. If we thinking back to the FEMA slide we saw, if we somehow stop wave attack and watch what happens. But in theory, the bluffs they'll still change, but they'll change in a slightly different fashion, in a much slower fashion. And one thing we'll see at the caveats at the end is we don't know how fast this process occurs, but essentially this is slope regrading. We go from a modern steep slope that was eroding, and eventually runoff and rain and wind will drive this towards maybe the watershed average, then to this geotechnical more gradual slope of 26.5, and then to a more gradual slope of 80.5. And then if we combine those two pictures, we get a picture that looks like this. So this is what our model does. We're kind of assuming we've got these two things going on at two different spatial scales, parallel retreat and slope regrading. And that allows us then to map out hazard areas on the top of the bluff. This V-Hep zone goes a little too far lakeward. It actually goes from the crest to the toe of the bluff. So that's a little long. We've got this is a very high erosion potential zone. We've got a high erosion potential zone. We've got a moderate erosional potential zone and a low erosion potential zone. So we've got 4 zones on our scheme, on our maps. Okay, and the widths they are ends up being essentially where these different slope angles intersect the tableland up here, and to which we add an average annual retreat rate number times a lifetime for a property, for a building. We'll see more of that in the maps in a second. It's conservative, definitely, because what's not known on the Great Lakes in particular is how fast slopes this natural regrading tends to occur. If you stabilize the toe, how long do you have to wait around before it becomes an 18 or a 26-degree slope? Not well known. So this is a conservative mapping scheme, as it were. So let's look at some maps next. We'll zoom into various parts of the coastline with just different background maps, just for context. And we'll look at what each of these zones tells us, some of its characteristics and so on. Okay, so here we'll just Move on to, we'll start off with the V-Hep Zone, so the very high erosion potential. That's the red zone on here. So it's located between the toe of the bluff, so down here at the lake level, and the crest. So this is the modern crest line running along here at the back end of it. And for, its instability is pervasive on these things. They're always moving, but as I said before, sometimes a property owner might say nothing's happened in 10 years, 20 years, but it's going to keep moving. You're just lucky that at your site, there was no movement for a few years. And here's an example of one of these places where we have lowland development at the toe of the bluffs that affects our index a little bit. This is either a prior slump from like the mid 1800s, or it could be a mini strand-plane deposit, a bit like a tiny Presque Isle. It's not exactly known how this thing is built. So construction in the red zone then is, because it's red obviously, is extremely risky. And this is the area that turns out to be regulated by BURSA in 1980 in all our municipalities. So basically you cannot build a house on this sloped surface, as far as I'm aware. We may learn more if there's any comments towards the end of the talk, but as far as I know, you're not legally allowed to put a building on this slope. It tends to be widest where it transects, where the bluffs are tall, right? It would make sense. Taller bluffs would give us a wider zone. Where the present bluff slope is less steep, because then thinking geometrically, it'll make this pretty wide from the shoreline, from the bluff toe to the bluff crest. And then where we have these large large paleo slums. And all I know is they're older than 1879 because we see them indicated on some of these T-sheets from our coastline, but it's unknown whether they occurred in 1850 or in 1650 or 1000 AD, but they're really old, long recurrence interval features that contribute to our index a little bit in terms of especially how wide the red zone is. Our high erosion potential zone is the next one landwards. That's the orange zone on here. It looks at least on this stretch of land, it's pretty narrow. You can barely make it out. So it's between the red and the yellow. It extends about 12 meters on average, or as much as 72 meters landward of the present bluff crest, the 2015 bluff crest. And its landward edge is defined by where this watershed slope average, this geometric thing, comes from, which leaves the toe of the bluff and comes up, and where it intersects the inland areas on top of the bluff. And then we add to that an average annual retreat rate, the long-term ones, that's that AOR 77, times 60 years. And we're using 60 just because it's somewhere, right now it seems like other Great Lakes states are moving to longer timeframes when they try and calculate setbacks. Historically, it's probably 50 years. Pennsylvania uses 50 for a residential structure. Other states are moving to 75. A lot of FEMA work involves a 60-year number. So that's how we ended up with that. So that dictates then where the landward edge of this orange or this HEP zone is. And what's happening here is erosion here is going to track landward from the lakeward edge, which is the modern day bluff crest, over the next 0 to 60 years. So it's eroding today, and over the next 60 odd years or so, we project that the crest will move across to the landward edge of this HEP zone. So construction here arguably is highly risky, considering this is about the lifetime of a house or half the lifetime of a house. And on average, for context, and the HEP zone lies lakeward of the municipal residential bluff setback distance in pretty well all of our municipalities. So, just for context, those of you know where that is, or familiar with that term, we're definitely in an area that the state would consider not wise to build a building, a structure. Our next zone landward is the yellow one, so a different background here to make it more jazzy, I guess, but that's our yellow zone. So here that zone extends on average about 28 meters back from the bluff crest to as much as 144 meters landward of the bluff crest. Its lakeward edge is defined by where this 26.5-degree intersect plane coming up from the toe of the bluff intersects the plateau. And then we add to that a longer time frame, because we've got to allow time for slopes to regrade, right? Times the average annual retreat rate. So this is like two home lifetimes, essentially, is what we're doing here. Bit arbitrary, but that's, if our first one was 60 years, building lifetime more or less, or 2 mortgages, here we're just doubling that. So the erosion will track across this zone anywhere from about 60 years out from now to about 120 years out from now. So you could argue construction here is moderately risky. You know, if you put a house on the lakeward edge of it, it's possible the bluff will get to that within the next 60 years. If you have a house somewhere on the back side of it, then you're obviously safer. So as we go through these various index strips, you know, it's always, if you think about it, it's wiser to not be in the red zone and to move to the green zone, or at least try and get to the landward as you can. Then for context with current regulations, the moderate erosion potential zone lies lakeward of the municipal residential BSD in about half of our municipalities. So as far as the state's concerned, you know, the setback for these municipalities on average is somewhere just landward of our orange line for over half the municipalities. And then our low erosion potential zone is our last one. That's our green one on here. So that extends from 60 meters back from the bluff crest. So again, the bluff crest is always at the landward edge of the red zone. It extends 60 meters back on average, or as much as 272 meters in some places landward of the present bluff crest, which is it's a big distance. That's it's about 900 feet. It's a long one. Its landward edge is defined by where we take this 18.5-degree slope and project it from the toe of the bluff up onto the plateau, and then add on the erosion rate. And this time, effectively about 200 years. So that's, you know, 3 times 60. So three lifetimes for a building. And for this, erosion will track across the LEP zone beginning in about 120 years from now. So a century out for about a century. So you could argue this is definitely a low risk area to consider having a building, right? Because erosion is not going to get there on average for at least about a century before it gets there. And then on average, the LEP zone lies lakeward of the municipal residential bluff setback distances in just one of the 9 municipalities. So this is like quite conservative, because the setback, maybe not for this particular municipality, the line might be crossing, you know, somewhere within our green zone. So it's a more conservative, conservatively safe area. So that's the quick run through on these zones visually, what they look like. And I think where it helps a lot is, you know, a property owner can look at their property parcel and see, you know, where the red, orange, yellow, and green zones are, and get a feel for, you know, how bad erosion is in their watershed. And again, these are all done by watersheds. So there's like 69 of them, as I said. So sometimes you'll jump from a very small, you know, total hazard zone over here on the top right hand picture, where the bluffs just happen to be getting low, to other places where there's a much larger width to those hazard zones. So we're looking at essentially mostly on this picture a bluff height factor is driving this, but also the watershed slope. What we're seeing here probably is the slopes over here on this watershed, this part of the watershed, are probably relatively low to begin with, so there's not going to be a lot of the geometric setback. So then some caveats. I mean, yeah, we're trying to like simplify a very complicated natural process with some very basic geometry. So some of the things we assume that obviously will limit how real or how true or how defensible indexes like this are, whether it's our coast or on the Oregon coast. I mean, we have to assume that hydro and geoenvironmental conditions during our time window when we collected data, so looking at bluff retreat between 38 and 15, all we can do is assume it's going to be similar during the next century to 2 centuries. You know, is that reasonable? Is it not? We could argue both sides of that argument, and all it means is, in reality, future crest retreat may be faster or slower than it has been over the past 77 years. And that'll just mean our zones may get wider or narrower, but we just don't know that. We won't know it until we look back from the future. We've got uncertainty in the retreat rates. When we compare the 38 data with the 15 data, it's about 0.13 meters per year, you know, when we map this stuff. And what that means is the inland limits then of the V-Hep, the HAP, and the MEP, they may get to their future locations, or in fact, they may intrude into the more landward zones as much as 1/8 or 16 meters once they get to those zones in the future. So there's a bit of uncertainty in the boundary, the landward position of those boundaries for those various zones, potentially as much as 16 meters for the MEP, but as little as 1 meter for the V-Hep zone. Future slope evolution timeframes are not well known. That's that stuff with the geotechnical angle of 26.5 or the sort of policy planning angle of 18. It's not known how fast slopes in our climate will, if we stabilize the toe somehow, will regrade naturally back to those much gentler slope angles. So that gives us uncertainty and again our boundaries for these V-Hep zones, but that's just a caveat of the model. Another caveat is we have some data gaps in some watersheds, just because we didn't have the older data didn't totally overlap with the newer data. That's sometimes an issue for bunches of transects, but that's solvable, going forward. If this thing was maintained, we could update, updating with new LiDAR, and we could, in theory, look back longer into the past using the 1879 Bluff Crest, which is mapped very coarsely. The Corps of Engineers also has that data set. But there's some, what I'm saying is there's some data gaps, but they're resolvable going into the future. And then the final point on this sort of index is an important one. It's definitely non-regulatory, so does not compete with what the state says is occurring on our bluffs. So I think it's a useful, non-regulatory, arguably conservative snapshot of relative erosion hazard on our coast over 1 to 3 building lifetimes. And it's based on 20-meter transects cutting across the bluff at more or less 90 degrees. So, we can only get down to resolution, maybe to property scale, and then we've also, you notice a lot of the maps we just looked at, it looked kind of smooth. We did a 30-meter smoothing on our data just so we had a much less spiky plot to our boundary when we plotted the boundaries to our zones. So we've done some smoothing. We've got 20-meter transects. It is a conservative snapshot. But the upside is, I think it will give property owners, a good visualization of where it's risky, obviously, on the bluff face, and maybe how far back they should consider building if they're going to be building a new residence or a business that's going to be on the plateau above the bluff for many, many decades, potentially a century or more. And that's our last slide. There's some references that will be on the taped version if you want to look at those at your leisure. But the highlighted blue ones this is the guys in Oregon who basically have a very similar scheme to ours. They developed it in the mid 2000 aughts, as it were. So there's more technical information in their materials. And then if we have time or you want to look at your leisure, this is the web link to the online map if you want to look at it. After this talk, it's relatively short address, pawalter.psu.edu. And you can zoom in and out and see, go to your area of interest and see how wide these potential erosion swaths are. Okay, so I think I'll stop it there. I think I've run out of things to say, and we'll just free up some time if we've got questions. We can, Sean, myself, and Mike can answer those as they arise. Thank you all for paying attention. Thank you.
Thanks, Tony. Appreciate it. We do have a couple questions coming in, so I'll just jump right to those. Clinton asked, are the watersheds at a Huck 12 level? Clinton, off the top of my head, I don't recall. I would have to go back and look at the metadata. So we contracted out the mapping services or the shapefile creation. So we worked with the firm Wolpert Inc. out of Ohio. Well, they're kind of everywhere, but we worked with that group. So based off the LiDAR data, they map the sub watersheds and the sub basins for us. So I apologize. I'd have to go back and look at the metadata. All these data sets, so all the data that was used, I'll just mention. So the watershed boundaries, stream files, crest lines are all available on POSDA, which is the Pennsylvania Spatial Data Access. So all these data are publicly available.
Yeah, Sean, I agree. So the Huck 12s, I mean, there's 6 in the West County and probably like 5 more in the East County, but we've got 69 of these. These are definitely sub-watersheds. Mm-hmm. So whatever Huck that is, I forget the correct term for that, not being a geographer. Whether it's a Huck 8 or a Huck 32 or something. I don't know.
A Huck Wolpert, right? Okay, and then we have another question here, Tony, from David. So I may have missed it. Is the AAR calculated based on measurements at the bluff crest or land water interface?
Yeah, that's a good question, because in the early days, there was, different places use different things to measure, but the standard now is going with the bluff crest. Whether it's here, California, Oregon, Wisconsin, New York, everyone's pretty well tracking the bluff crest. So that's what it is. We can get, off the LiDAR, that nice sharp bluff crest in most cases, and then off the older data sets, potentially going back as far as the T-sheets, where it gets obviously quite hard, but aerial photography, it's the bluff crest. They end up going with the bluff crest, I think, over time, because it's easier to pick that out than it is to pick out the bluff toe. And then also people, living on a coast, they see the bluff crest, they know what it is, they can picture how it's retreating. Because if you know a bit about coastal geology, what's going on the bluff toe can be quite different to what's going on the bluff crest, because we've seen that in a different project where some of the sediment being lost off the bluff crest actually sits on the toe sits on the bluff face for a while, and doesn't necessarily cause a change to be seen on the bluff toe.
Okay.
And actually, it also makes more sense because the bluff toe is where we would accumulate and lose beach material on a regular basis and slumped material coming down. So it'd be way more variable, I would think, just because of those two other things happening: literal transport building up the beach on the toe, and then slump material falling down the toe and lasting maybe a year before waves wash it away. It's just you're not really measuring as precise a bluff face feature as the crest would be.
Thanks. And as we go through and answer these, if it's not the answer you're looking for, feel free to ask a follow-up question or clarify. So next is, so I may have missed it, this is from Brian, but are there known speculated causes of the historic mega slumps, and any projections of these kind of events happening in the future?
Yeah, that's another good question. Yeah, there's the short answer is no. That's it. But the long answer is, yeah, they're big. Some of them go back, I think, is it 50 meters, 70 meters? They're big. The biggest slump we'll see happening during a year or during a spring season might jump back 20 meters. So these mega ones go back 50, 70, I think 100 in our biggest one. And there's no known cause for these things, let alone how old they are. But they could be anything from, seismic. We do get seismic activity here, like California and Oregon. They could be triggered by shaking events or just an extra wet year, so extra groundwater flux coming out through them. There's no definitive answer on that, even though it's a very good question. And then also, how frequently do they occur? And that's an unknown. And it is also in Oregon and other states. We see them. We know we can track them back as far as the oldest data set we have, which is going to be a T-sheet somewhere in the 1800s. But then it's hard to tell how long they've been there before that. And it's also possible they start off as pretty small regular slumps, and then they cause, this is work that was done in Wisconsin, don't want to blank on the name, but once you develop an embayment, like a rotational slump feature on a bluff face, it tends to entice groundwater to flow towards that embayment. It's called groundwater focusing. So then you'll start getting more groundwater pumped out through that feature, and that makes it grow even faster. So interestingly enough, the biggest ones on our East County that might be now 200 meters across, there's active groundwater coming out through them. So it's feasible they started a long time ago as a regular, maybe with a recurrence interval of like 5 or 10 years or 15 for a regular small rotational slump that somehow attracted enough groundwater that just kept growing and growing by groundwater sapping and became the monster features relatively that they are now.
Thanks, Tony. And switching over to the Q&A. So we had a couple questions from John Dedish. So the first was looking at the ravine slide where a stream comes in. Do you expect perpendicular erosion?
Oh yeah, that's a good question. So exactly, yeah. So this project was focused on, so I've got the screen on if you can see it, on lakefront bluff retreats. We didn't look at what's happening on the ravine sides. So that is definitely occurring, exactly. They tend to be more, all the ravine slides are way more stable than the lakefront bluff face. Not just because, for the most part, there's no wave activity trying to push that whole profile landward all the time. So in theory, on this slide, for example, all our zones take a sudden, nice, clean end along a transect, but in reality, all those zones should, in theory, wrap around if we're interested in tracking what's going on within the ravine sides, which would be at a much slower rate. Our hazard zones would be much narrower because the retreat rate would be much slower. Conversely, our ravines tend to be pretty steep. That's the other thing. So you might have the geometric slope part of the thing, making those zones a little wider. So yeah, they're purposely just left out of our scheme because it wasn't required for the lakefront retreat. That's a good catch. I forgot to mention that.
Yeah, that's a good question. His follow-up, does this work relate to river bluffs?
Short answer is no. So just basically, yeah, we just ran through. Yeah, I mean, it'd be interesting to do because this could be done. You know, there's potential for looking at, you know, smaller scale, look at picking a couple of watersheds and doing a smaller scale study, you know, to see how those ravines change over time. But then the problem is, you know, there's a limitation in how old the data is that we can compare it to retreat rates to. Like usually on T-sheets, if they even drew in the ravines, it's going to be very inaccurate. And aerial photography gets a little harder because you've got all green tree vegetation above the ravine, on the ravine crest, and down in the ravine. Where at least on the lakefront, you've got a lake out there. It's, you know, there's you get visual assistance in picking where the bluff crest probably is in the aerial photographs.
Thanks, Tony. And then I think feel free to, we do have a couple minutes left. So feel free to keep asking questions. Again, we'll answer as many as we can. So I don't know if this is definitely out of my area of expertise, Tony, this next question, and I'm not sure if you're comfortable answering or if we want to just refer to them to the coastal management program. But one of our attendees was mentioning different types of, you know, barriers for protecting bluffs.
Yep.
And they wanted to know what is the best, you know, bluff protection.
Yes, that's a good question. That's a complicated question to answer. And again, if I don't answer this well, I mean, the Pennsylvania Coastal Resources Management Program are the go-to people on this question. But if you live on a bluff coast, you know that various solutions have been tried, and they work to varying degrees. I mean, so let's see, you can build an offshore structure. They've tried those in, it turns out Illinois seems to be very content with the success of their coastal engineering on their bluff coastlines, because their approach is to, they're less concerned with keeping a natural looking bluff, but with stopping bluff erosion. Because I think historically, a lot of their bluff erosion occurs on the north side of Chicago, which is one of the wealthiest parts of the state. So there's a lot of vested taxpayer interest to stop the erosion. So they basically, Illinois has a penchant for putting in breakwaters so offshore breakwaters or breakwaters that extend out from the shore, and then behind it you can build a marina and you can build some beaches. So what you're doing is you're taking the wave attack away from the bluff. So when you think of it that way, physically, it sounds like a good solution because you're taking away one of the causes. And then all you're left with is other stuff like groundwater seepage, surface runoff, wind attack, if that's significant. So if you isolating the toe is a good thing to do because nature does that. We've looked at what's happened to bluffs in the Chesapeake where for various reasons, a lot of sand accumulated. It was actually usually updrift of jetties for inlets. And they've noticed that where bluffs have been separated from the Chesapeake Bay waves for like several centuries, the bluff retreat has seriously slowed down. So I think that's the key thing, just getting the waves away from the toe. And whether that's putting in, you know, a lot of rubble. I'm thinking of the north side of Chicago, there's the name of the place, I'm drawing a blank. The various parks, all the little towns that seem to have park in the name, but you could Google it and zoom in, you can see there's some very beautiful looking structures with contained beaches inside them and boating marinas, and their retreat rate, their bluff retreat has slowed down because they've taken away half the cost. Other stuff, I mean, putting toe protection on your bluff, I mean, there's a lot of it in our county. I mean, it does buttress the slope, it provides mass and retention capability right at the toe, and that will stop stuff sliding off the bluff. But then that material then always has a lot of pressure behind it from the mass of the bluff behind, trying to push it out and make it fail into the lake. So personally, I would think that's less of a workable solution over the long term than somehow putting in structures like artificial beaches and breakwaters on the shoreline. And let me see, you can think of Presque Isle. I mean, our Presque Isle landform, which is this guy right here in the center of the picture, we tend to see lower retreat rates in our Presque Isle Bay just because, you know, it's a relatively shallow patch of water that doesn't have big wave activity. We've got this thing almost, you could argue Presque Isle is a structure that protects this coastline from wave attack. And that's, you know, part of the reason why retreat rates on our hazard zones are narrower along the city of Erie lakefront than they are to the updrift, especially, and then downdrift down here. There's probably a bit of shadowing benefit occurring just immediately downdrift of Presque Isle because the waves don't wrap around sufficiently to cause a lot of damage here. But so if you need more information on that, I'd say the CRMP people are the place to go for the latest sort of state recommendations on that. And also look at Ohio. I mean, Ohio seems to be very, what's the word, straight up or always considering coastal engineering to protect your bluff. You know, they realize that if we graded and put in like one of the diagrams from way back here, put in toe protection, you know, like here, regrade the slope, that will give you, you know, a stable slope for at least for the life of your house, maybe 2 or 3 house lifetimes. So you can find information on the Ohio DNR site as well. And I'd also look at the Illinois DNR site for, you know, how well they think solid, you know, construction engineering on the toe actually works over time. It's a long answer, but sorry about it.
Thanks, Tony. I appreciate it. And just to follow up, and I think you kind of answered this, does PA allow toe armoring?
That's a question for CRMP because I mean, it exists on our shoreline, right? At the toe of the bluffs, there's a lot of historical, there's steel walls, there's various crib designs, there's jetties near the river inlets, there's groins, there's beach backfill. There's recently a house went in out near Vonia where they put in a whole series of terraces, like a rice paddy, a whole series of terraces, and the house actually sits on the former bluff. But I'm not sure where the state is now on whether and how or what allows them to or not allow them to grant construction of shore protection on the lower bluff.
Yeah, great. And Samantha Burton with Coastal Management Program, she just put in a link in the chat box to more information with their program. So any of the policy regulation type questions, I would refer you to them. They would be the best, I think, source for the right answer.
Yeah.
And then we do have one more question coming in here, Tony. So if erosion is reduced and toes are armored, how is sand sediment movement impacted in the system? Is PA seeing issues with beach nourishment?
Good question. It's a good technical question. Yes, so in theory, if we anchor, if you can see that Ohio slide we're looking at, if we like put toe protection on the toe of the bluff, and that's large, you know, 2 to 4 ton armor stone, and if we put in wells, for example, in the top half of the bluff to drain some of the groundwater to stabilize that material, obviously we're stopping a sediment supply coming down to the littoral zone. And we've noticed that in work in the West County, when we look at the work we did and then also prior research, I think the general consensus is of all the sand moving in the littoral zone along our coastline, it's 95 to 98% of it comes from the bluffs. They're a very important exporter of sediment. So if we basically protect them from erosion, we protect that sediment coming in, and then that allows erosion to occur on bluffs that maybe aren't protected further downdrift. Or it might, if we're updrift to Presque Isle, it would limit sediment supply to Presque Isle. I mean, the number generically, I think, is about 30,000 cubic meters a year of sand comes into Presque Isle per year. That helps keep the beaches the way they are, but then we also add nourishment. So if we buttressed all or protected all our bluffs, that's 30,000 cubic meters of sand gone away that has to be replaced by buying nourishment to take its place. So yeah, it's an interesting question. Some states like Washington State, they do not want to protect their bluffs purposely because they know they supply so much littoral sand. So Puget Sound has got you could probably Google this term. It's a feeder bluff, like Google the term feeder bluff. They've got a whole program where they try and conserve as much bluff as possible in as natural a state as possible, allow it to erode because then their beaches stay beaches. You know, the sand is still being supplied. It's like a lot of stuff in nature, you know, so to have a certain benefit in one area, we got to have like a cost somewhere else. And here you could argue philosophically the bluffs do a very good job of giving us nice small pocket beaches. I mean, they're not great in Pennsylvania, but allowing Presque Isle to persist. You know, it's a trade-off, and a lot of environmental stuff is like that. We also happen to have a big marina updrift of us just across the Ohio state line. Historically, that's trapped a lot of sand. And that's sand that would have come down our coast. So CRMP would also be a good group to ask, get more information on that, because there's numbers. Conneaut Harbor does deprive us of sand, but you know, going forward in the future, I think there may be more artificial bypassing of sand around that structure, possibly by truck or by pipeline to get that littoral sand moving towards our coast. So obstructions on coastlines generally are not good either, in addition to whether we're, you know, armoring the toe on the top and taking out water and changing grades. So yeah, so it's a good question. There's trade-offs on both sides. We save the bluffs, our beaches will probably suffer. If we allow our bluffs to erode, we still have beaches.
Thanks, Tony. And in the chat, I put, our fourth webinar last year, Tony talked about, you know, sediment supply as a result of bluff retreat in West County, or the western end of Erie County in Pennsylvania. So I do encourage you to look at that in associated study. So we're gonna have one last question. This comes from Tim Bruno, so I have to ask it. Tim Bruno is Chief of Office Great Lakes, and he was the grant manager on this project as well. And he asked, can you briefly explain how the nearshore bathymetry, specifically the shale underwater ledge, could cause material to be removed from the littoral zone, and how that might affect wave energy and bluff toe erosion?
Okay, so read that one more time, please, Sean.
Yeah, sure. And it is in the chat if that's easier for you to open the chat and read it.
Okay.
So towards the bottom.
Okay, I see it. Yep.
Yep.
Okay, so yeah, so it turns out our shoreline, most of it, our near shore is shale bedrock. It's got a veneer of sand and gravel and stuff that basically moves along all the time. We've got shale bedrock in the near shore, across the surf zone, and then a lot of our bluffs as we climb up the bluffs for a meter or two or seven. So on the onshore part, you know, the shale bedrock is compared to the glacial tills and the sands, is very resistant to erosion. Because of that, it tends to form almost vertical walls, or very steep bedrock walls, and so then it becomes like an engineering steel wall. You know, in the way it works, waves coming in will bounce off that shale face, bedrock face, and then they will reflect back out into the water, and you see that on say seawalls down on the bay side of Presque Isle when the storm direction is the wave direction is correct. So you'll reflect the waves offshore, but you also reflect wave energy downward, and that will do is it'll scoop up any loose material and drag it offshore. So a vertical wall, whether it's shale or an engineered steel structure in Illinois, they're notorious for doing that, for allowing material to be dragged off away from the toe of the bluff. In the near shore, I'm not sure how that works. I mean, we've got shale in the near shore, the waves come in, they move the sand along. I would think the roll out there is less problematic, because all the sand is moving anyway, whether it's a sandy bottom or a till bottom or a shale bottom, it's going to be moving with the littoral current along the shore. So I don't think there's much of an issue with that. I mean, arguably the shale is a benefit offshore, because if we were in Illinois, on the Illinois coast, they don't have a shale bedrock near shore. So what happens is their near shore is also eroding, which arguably ours does not. Okay, so during over time, then their lake bed gets deeper near the shore. That in turn allows larger waves to get in and attack the bluffs. And when I used to work for Illinois DNR a long time ago, at one point the Corps was considering paving with brick or similar material the surf zone in parts of the northern Illinois coast to see if it would be a good way to prevent this nearshore down cutting, because that steepens, otherwise you're steepening the profile and you're allowing bigger waves to do more damage. At least our shale nearshore stops that just because it erodes so slowly. A big wave coming in will trip up over the shallow water and dissipate a lot more energy than if it was passing in over soft glacial tills that it could remove on an ongoing basis. And apparently, even during, low stands of lake level would be good for us because it takes wave attack away from the toe. Whereas in Illinois, they recognize that low lake levels actually allow waves to do more damage on the nearshore lake bed. So when lake levels eventually rose again, you could now have larger waves getting into the shore than did, say, 10 years prior during the prior high stage. So I think most of the effect would be at the toe of the bluff itself, where we tend to have, it's almost like a wall of shale along much of our bluffs. That's a good stabilizing feature for our bluffs, but it does have an effect of enhancing sand removal from the toe of the bluff and sending it offshore a bit. But at least it's going to the littoral zone and it'll head down drift and maybe benefit someone else.
Great. Thanks, Tony. Well, we are at time here. I do appreciate the discussion and the thoughtful questions. And Tony, good job answering those. So again, I wanted to thank everybody for attending today's bluff session. We really appreciate you spending an hour plus with us on this cold Friday afternoon. Again, if you have any questions, feel free to reach out to Tony, myself. Also want to thank Dr. Neighbor, Penn State Barron, who was on this call as well, who did a lot of the background GIS work on this project. So if you have any questions related to the geospatial analysis we did, or the geology work, or the bluff mapping application, feel free to reach out to our team. We're happy to work with you and answer any questions you might have. And have a good weekend, everyone. Thanks, Tony.
Thank you very much.